Hello, I am Sam Zhang and this is my lab report for Lab 5 for Physics 2211. And for this lab, I modeled the motion of a falling slinky. So the purpose of this lab was to investigate this motion and as well as create a computational model to figure out exactly why the bottom of the slinky remains relatively stationary until the slinky kind of collapses. So the overall results for this lab was relatively successful. I was able to create a computational model that very closely matched with the real world results where the bottom of the slinky remained relatively stationary for a while. So we're going to begin with some assumptions for the model. We're going to assume no friction or air resistance, and we're going to divide the slinky into many segments of connected springs, and each of them with the same spring constant and mass, and we're going to also assume that there are no external forces. So for the theoretical model, we can model the points of the spring segments as point particles, and when we increase the amount of point particles, we get closer and closer to the real system. In fact, if we increase as the number of point particles approach infinity, the particles effectively form a line, which can basically become the actual slinky. So for a certain point particle on the segment, we can derive this vector equation from the gravitational, spring, and damping forces that affect the point particle. And after using some equations relating to stuff like, for example, the spring the damping ratio, we can arrive at this final equation that describes the acceleration experienced by a certain point particle on the spring. So we can therefore find that a certain point particle's acceleration is based on the distance in relation to its neighboring point particles, as well as the velocity difference in relation to its neighboring point particles if damping is considered. So because of this, the points on a slinky experiences a delay because its acceleration is based on the physical characteristics of the particles surrounding it. So here are the initial conditions. I have the first particle placed at some point, a total of 11 point particles for 10 springs that are connecting each of them, and I have the positions of each of the following particles just placed where the static equilibrium would normally occur. So for my code, I begin with some constants. I then had some varying controls that control stuff like, say, damping, as well as some code breaking mechanisms. And then I modeled the initial conditions of the point particles, as well as the springs here. And then after I just also, for useful information, I modeled the center of mass as well as a camera point of view. Then I used a time update formula, and inside the time update formula, I first calculate the vectors relating to the positions, and then I used those to calculate the spring force, and then I also used it to calculate the damping force as well. And then I calculated the net force, and then I used the position and velocity update formula to find the new positions of each point particle based on time. And then I also did some equations relating to collisions, as well as updating the center of mass, as well as the camera point of view. And finally, I also just had some equations here that would allow me to print out some useful information if I ever need them. Okay, so here is the video for the computational model. You can see that the slinky, especially the bottom, remains relatively stationary until the entire slinky collapses as it falls. So here is the raw data that I have. And here are my combined graphs of the positions of the particles over time, the velocity of the particles over time, as well as the acceleration of the particles over time. You can see that the bottom slinky point particle hardly moves until the particles above it has reached or surpassed its y position, as well as the fact that the acceleration data shows that the acceleration of the center of mass is equal to -g, which we would normally expect. And for our discussion, the first question is, what if we change the amount of damping on the spring? So because the amount of damping is based on the velocity difference between the two ends of a spring, with the damping force resisting this velocity difference, a stronger damping force would probably make the bottom particles start moving quicker, as there is more resistance to this delay, which causes the point particles to have different velocities. And we can see using this graph that when we vary the damping ratio, that when the damping ratio is higher, or the particle experiences more damping, that the bottom particle accelerates more quickly. And second, by the delay in the slinky, we would mean that the acceleration of the spring is based on the position and velocity difference, and again, because of that, for a part on the slinky to move, the parts above and below that point have to move first. And this is why the bottom of the slinky stays in place for a duration of time, because its surrounding parts have yet to start moving. And again, and I would say that this delay might have some interesting connotations with spring waves, which would be a very interesting area for further exploration. So in conclusion, I made a computational model that models this slinky. The bottom of the slinky stays relatively in place until the rest of the slinky fall close to where the bottom is, and increasing damping decreases the amount of delay that the bottom of the slinky experiences. So thank you for watching.